All right, today in CHEM100, we're going to review materials for Exam 6. That's Chapter 15, and the topic is solutions. So let's get started with the review document, and you'll notice there's some of them highlighted. Those are the ones I want to cover today. Starting with number 1. How many grams of calcium chloride are needed to prepare 5.17 liters of a 0.5 molar calcium chloride solution? Go back to the definition of molarity. It's moles per unit volume. So if the question is how many grams of calcium chloride, we can't go directly to grams here. But if we can find out how many moles we need, then we can convert moles to grams. All right, so information we have given, 5.17 liters here. 5.17 liters, and that is in the correct units, needs to be liters. And we need a 0.5 molar solution. So our unknown is the number of moles. So all we have to do is multiply 0.5 times 5.17. That will tell us how many moles of calcium chloride we need. And that's 2.585. So the number of moles equals 2.585 moles. And notice we have 3 significant figures there, 3 significant figures here, but I kept 4 here for the express purpose of reducing the possibility of rounding errors. We will round at the end. So we want to convert those moles to the number of grams. We need a conversion factor that will cancel moles and leave us with grams. And like I said before, if you have grams and moles in a quotient relationship, that's always molar mass. And it's given, molar mass is given there at 111.0. So all we have to do is multiply 111 times that, and we get 28.694 grams, and we're going to round it off to 3 places. 28.6 grams. That's what we need. Oops. My mistake. Got my decimal in the wrong place. Let's try this again. 694. 694. 694. And it's, there we go. Okay, so we rounded off to 3 is 287 grams. There we go. So that would be B is the answer for that one. All right. Number 2. What mass of solute is contained in 64.9 milliliters of a 2 molar sodium bromide solution? Okay. So we still have this relationship, and we're looking for mass of the solute. We probably should solve this equation for moles, because then we're going to have to convert moles to mass. And so if we solve it for moles, we have molarity times volume. Okay, so what's the molarity? The molarity is 2 molar. And the volume is 64.9 milliliters. How many liters is a milliliter? Right? Remember, I've told you, if we want the units to become bigger, milliliters is small, liters is big. If we want that to become bigger, then this number has to get smaller. So if you're going to move the decimal place to give you liters, you want to move it 1, 2, 3. 0.0649 liters. You can do it that way, or you can use dimensional analysis, and you can say 1,000 milliliters per liter, right? 1,000 divided into this gives you that value. Okay, so that's the volume, 0.0649 liters. Okay, so 2 times 0649 is 0.01. Oops, excuse me. 0.1298 moles. Now we want to convert that into mass of sodium bromide. Okay, here's where you're stuck. If you don't know how to write sodium bromide formula, then you cannot determine its molar mass. Sodium is an alkaline metal. Bromine is a halogen. Okay. So that's the formula. 1 and 1. Okay, now we can do the molar mass. Sodium, look at your periodic table. Sodium is 23. And bromine is 79.9. I'm 2.90. So if we want to convert these moles to grams, we need to put that number right there. 102.90 is 13.356 grams, or let's see, 3 significant figures. So we need to round it off to 13.4 grams. And that would be, B would be the answer to that. All right, that was 2. Let's scroll it up a little bit to 3. Looks like I've got a note to myself, continued in number 6. That means number 6 is based upon the same scenario here. So let's do 3, and then maybe we'll skip to 6 so we don't have to erase everything and rewrite it. All right. You have 3 liters of 3.67 molar solution of sodium chloride. That's called solution A. All right. So solution A is 3 liters of 3.67 molar sodium chloride. Okay. You also have 2 liters of a 2 molar solution of silver nitrate. So solution B is 2 liters of 2 molar silver nitrate. Okay. You mix these solutions together to make solution C. What's the concentration and molarity of the silver ions in solution C? Okay. We're going to mix these two together. That means there's going to be a reaction. So you need to know the right, you want to write the reaction. All right, what's going to happen? Well, silver is going to possibly react with chlorine. Okay. Now, the next question is it going to stay in solution or is it going to precipitate? And if you look at your chart, right, you remember that chart I showed you? Let's see. Here it is. This one right here. So you find silver across the top, you find chloride down the side, you run across until they meet and see if it forms a solid, a precipitate, or if it stays in solution. If the box is clear, it's in solution. If it's grayed out, it forms a solid. And you'll find that this forms a solid. What's left? Sodium and nitrate. Do the same thing and you'll find that sodium and nitrate are in solution. Okay. So here we have a reaction and we're trying to find out how much of this is left in solution. Because what is this? Silver nitrate is soluble, which means it produces silver ions and nitrate ions. Okay? So, if we're going to assess the stoichiometry of this reaction, we need to know how much of this we have, how much of that we have, and then find out which one is limiting. Okay? So, this is solution A. We have 3 liters of 3.67 molar. So remember, moles equals molarity times volume. If we multiply these two together, we'll get the number of moles that we have available in this reaction. So that's 11.01 moles of sodium chloride. And we'll do the same thing here. 2 liters and 2 molar gives us 4 moles of silver nitrate. Okay, first of all, one thing we didn't do is balance the equation. Let's check to see if it's balanced. 1 sodium, 1 sodium. 1 chlorine, 1 chlorine. 1 silver, 1 silver, 1 nitrate, 1 nitrate. So this equation is balanced as written. That means for every one of these, you need one of those. Right? So if you need 4 moles over here, then you're going to have that much of sodium chloride remaining, and all of this is used up. This is the limiting reactant. This is the excess. All right, so for solution C, when you put them together, how much silver ion will be left? 0. None is left. It's all gone. You used it all up. Okay? So the answer for 3 is C. 0. There's no silver left. All right. Let's move to number 6, and it probably uses this same scenario. There we go. 3 liters of 3.48. Okay, it's slightly different. So we need to make some modifications here, but it's based upon the same reaction. Let's see, 3 liters of 3.48. All right, 3.48 now. Oh, by the way, this is 6. There we go. 3 liters of 3.48 and 2 liters of 2 molar. Okay, so that's the same. Mix the solutions together. Now they're asking what's the concentration of sodium ions. Okay. Well, in this case, we know that sodium is in solution here as ions, and sodium is in solution here as ions. It did not precipitate. So the concentration of sodium is dependent upon, one, the total moles of sodium that went into the reaction divided by the final volume. That's the thing that changes. The number of moles of sodium did not change because we got no reaction with sodium and other elements. We just put them together because they're a cation and anion. But the concentration of sodium now is going to be, this is 4.8. 4.8. The total moles of sodium would be 3 times 3.48, which is 10.44 moles of sodium ions. And that's the same sodium ions that's over here once we put them together. What's the volume, though? The volume now is 3 liters plus 2 liters, or 5 liters. So we divide by 5 and we get 2.088 molar, or let's see, we really only have 3 significant figures, so that's 2.09 molar sodium in aqueous solution. Okay? And that answer would be D. Okay? Oh, I got another message directing me to number 47. Maybe we're using similar scenario for 47. So let's go down to 47. We'll get there eventually. Here we go, 47. All right. So let's remove this. Let's change this one to 47. There we go. And let's check our conditions. 3 liters of 3 molar, 3 liters of 3 molar sodium chloride. So now this is changed to 3 molar. There we go. And we've still got, and we got 2 liters of 1.84 molar silver nitrate. 4 molar. There we go. All right. So we don't know if this is still true. So let's erase that part. Okay. And let's change this part. All right. And to 1.84 molar. There we go. Okay, now we've got new conditions for number 47. Mix these two together. Now the question is, calculate the concentration of nitrate ions. This is similar to number 6 because nitrate is also still in solution. We just need to know what's the how many moles of nitrate and what's the final volume. Right? So moles of nitrate would be 1 to 1, so 2 times this, 2 times 1.84 is 3.68 moles of silver nitrate which is also equal to 3.68 moles of nitrate ions, because they're 1-to-1. Now we just divide by the final volume, which is 3 and 2, 5 liters, and we'll be able to calculate the nitrate concentration. Okay, 0.736. Yep, molar. That's C. The answer to this one is C. All right. I got another note. It says go to 52. So we're probably using the same similar scenario. Yep, solution A and solution B. Okay, so 52 is right here. Okay, and let's see. We've got 3 liters of 3.77. 3.77 molar sodium chloride. Okay, and B is 2 liters of 2 molar. So we're back to 2 molar silver nitrate. There we go. All right, so we need to change this one. And we need to change this one back to 2. And erase all this stuff. There we go. Now, what's the question? Calculate the concentration of chloride ions in solution. All right, now we can find out, we need to find out which one is limiting again, just to be sure. If it's the same, that's fine. Right, this is 4 moles, right, of silver nitrate. And this one is 3 times 3.77 is 11.31 moles of sodium chloride. Okay, so we have this similar situation. 4 moles here, and it takes 4 moles here because 1-to-1 relationship. So we need to use up 4 moles here. 1, 3, 7. That much sodium chloride remains. Okay, some of the chloride was used up to make this compound, and the rest of all the sodium is over here. Right, so that means this many moles of sodium chloride means 7.31 moles of chloride. Right, because it's 1-to-1. For every 1 sodium chloride, you get 1 chloride. So we have the same number of moles of chloride. Now, the question is, what's its concentration? We're in a similar situation. We need to divide moles by volume, right? Molarity equals moles divided by volume. So moles divided by 3 plus 2 is 5 liters. So 7.31 divided by 5 liters is 1.46, rounded off, molar chloride. That's D. D is the answer. Okay. So I didn't write it up here again, but this is limiting. And this is excess. Okay. All right. Now we can go back and pick up where we left off. Okay. Let me see if I can get this thing to scroll faster. Yeah, there we we go. Now we'll get back down. That was 3, we went to 6. So now we're picking it up with 4. Okay. Number 4. Number 4. The molarity of chloride in 110 milliliters of a solution containing 3.22 grams of calcium chloride is the molarity of the chloride ion. So how are we going to solve this? What's the question? Well, the molarity of chloride, obviously. But what's our process? How are we going to solve it? Well, in order to find the molarity of the chloride, we need to find the molarity of the calcium chloride first. Then we can infer or calculate chloride concentration from that. So what are we given? Well, we've got the formula. We've got the mass, which is 3.22 grams, okay? And we have the volume, 110 milliliters. Milliliters, okay? So we got the volume, only it's not in the right units. So this would be what? 1, 2, 3. 110 liters. How about this one? We need moles, don't we? Grams on the bottom cancel. There's moles. So grams per mole is what we need for calcium chloride. All right, calcium is 40.08. Grams per mole. Chloride, we need 2 of them, and that's 35.45. Okay, so let's do some calculation here. 40.08 and 35.45 times 2, add that together. That is 110.98 grams per mole. Okay, 110.98. We're going to divide that into 3.22, which is 2.90 times 10 to the minus 2 moles. Okay, now we can calculate the molarity of calcium chloride. Right? So the molarity of calcium chloride is equal to 2.90 times 10 to the minus 2 moles divided by 0.110 liters. And I get 0.264 molar calcium chloride. Okay? That's the molarity of this formula. What's the molarity of the chloride ions? Well, look, for every one of these, you get 2 chlorides. So the chloride concentration will be double, be twice as much. So we'll have 0.528 molar chloride ion. Okay, that would be, your answer would be C for that one. All right, that's 4. And 5, yes, 5. Get my cursor out of the way here. Number 5. What volume of 12 molar nitric acid is required to prepare 6.71 liters of 0.1 molar nitric acid? Okay, this should be obvious as a dilution problem. We're going from a concentrated nitric acid solution of 12 molar down to a 0.1 molar nitric acid solution, a diluted volume, a diluted concentration. Okay, so when that happens, when I've recognized it as a dilution problem, I like to set up a table, right? The molarity of the concentrated, volume of the concentrated, molarity of the dilute, volume of the dilute. And put my values in here before I try to solve the problem. That way I don't put the numbers in the wrong place. So what's the molarity of the concentrated? Well, it's 12 molar. What's the volume of the concentrated? That's the question. How much of that do you need to dilute to make the new solution? Right? So what's the final volume? 6.71 liters. And the final molarity is 0.100 molar. Now we're good. Now you can use the formula. Molarity of the concentrated times the volume of concentrated equals molarity of the dilute times the volume of the dilute. So now we can put the values in here in their proper position. Right? That's unknown. And this one is 0.100 molar. And this one is 6.71 liters. Okay? So the volume we want is this one times that one, 0.1. I'm going to leave the units out. We already know we got the right units. 0. Okay? This one becomes a divisor over here. So that will solve the problem and give us the number of liters of the concentrated that must be diluted to that volume to give us this concentration. And I get let's see. Their answers are in standard notation. My calculator gives it to me in scientific notations, so I got to translate. All right. So I've got 0.0559. 3 places. Liters. 0.559, which would be A. That's how much of the concentrated we need. Now, who measures in the laboratory, who measures things in liters? Well, when you need small amounts, you don't measure in liters, you measure in milliliters. So just out of curiosity, how many milliliters is that? All right, 1, 2, 3. Remember, the units are going to get smaller. Liter is a big unit, milliliter is a small unit. So if we go from big to small, then we go from small to big. So 55.9 milliliters is the volume we need. That's not part of the problem, but I couldn't resist. Okay, that was 5. Let's scroll to the next one. We did that one already. Okay, so we'll move on down to number 9. Let's see. I'm going to scooch this over a little bit because it's cut off on the side. There we go. Number 9. You have 3 ammonium sulfate solutions on the lab table in front of you. All right, and it gives you those solutions down below. All of the solutions came from a 500 milliliter volumetric flask containing 3 molar ammonium sulfate. Then the problem below specifies that we're looking at solution 2. How many moles of ions does solution 2 contain? Okay, so we only need to focus on solution 2. Right? What are the conditions for solution 2? 68.7 milliliters. The volume equals 68.7 milliliters. Have 3 molar solution. So the molarity is 3 molar. And the compound is ammonium sulfate. ammonium, right? That's one of your polyatomic ions, +1 charge. And sulfate, right? +1, -2. So how do we write this compound? You need 2 of those. Okay, that's the compound. If you can't write it, you can't answer the question. All right, so the question was, how many moles of ions? All right, so we need how many moles of that are there first? Then we can do the ions. All right, so liters is going to be 1, 2, 3, 0.0687 liters. So now the moles is M times V, 3 molar times 0.0687 liters. And that's how many moles of the compound. Times 3. So we have 0.2061 moles of this compound. There you go. Now, when that goes into solution, and it is soluble, you can look it up in your table. Ammonium plus sulfate is a soluble compound. So it's going to produce ammonium ions and sulfate ions. Right? It's going to break up into in aqueous solution, it actually breaks up into 2 ammonium ions and 1 sulfate ion. So how many ions are there for every one of these? There's 1 plus 2 is 3. 3 ions per mole of compound. 0.61 moles of ammonium sulfate. Okay, so for every 1 ammonium sulfate, you have 3 ions. 3 ions. So 3 times 0.2061 will give us the moles of ions. So we get 0.6183 moles of ions. Let's see, we have 3 significant figures, so we have to round that down. 0.618 moles. 0.618, which is E. That would be our answer. Nine. Let's see. Let's clear the board. And scroll to the next one. Number, let's see, can we get 11? Yeah, 10 and 11. Look, 10 looks like it's just definition. So a mixture of sand and water is what? A mixture of sand. Is it going to settle out? Yeah, it's a suspension. It's not a solution of any kind. It doesn't designate a solute or a solvent because you have to be a solution to have those. So a mixture of sand and water is nothing. It's none of those. Right? The answer is E. It's none of those answers that are given. About 11. A chemist needs 225 milliliters of 3.1 molar hydrochloric acid. What volume of 12 molar must be dissolved in water to form this solution? Okay, ignore significant figures for this problem. Okay, we can do that. A chemist needs 225 milliliters of 3.1 molar hydrochloric acid. This is a dilution problem. Concentrated, concentrated, dilute, dilute. So what's the concentrated? 12 molar. Okay. What's the volume? What volume of 12 molar? That's the question. The final concentration is 3.1 molar hydrochloric acid. And he needs 225 milliliters. Right? Our answer is in milliliters. So, if we set up our formula and put in the values, 12 molar, the volume we need, this is 3.1 molar. And if we put the volume in as milliliters here, then it has to be milliliters there. This is a ratio. So we can put in 225 milliliters here and solve for this one. This one times that one divided by this one. And 12. So the volume that we need is 58.1 milliliters. Any one of those close to that? Yeah, E. E is very close to that. That's our answer. All right, that was number 11. Scroll to the next one. Number 13. Yeah, we can get both of them on there, 13 and 14. Okay. Let's say you have 250 milliliters of a 4 molar sugar solution. You add 376.3 milliliters of water to this solution. What's the concentration of sugar now? Well, on a qualitative level, if our initial concentration, let's see, our initial molarity is what? 4 molar. Okay, and we have an initial volume of 250 milliliters. Right, 0.0. Right. What's going to happen when we add more water to it? Right? What is the water? Water is the solvent. Add more solvent, the concentration of the solution decreases. Okay? So what we're adding is the volume added equals 376.3. 376.3 milliliters. Okay, so if we're going to calculate the new molarity of our solution, we need to know the number of moles of sugar and the final volume. How many moles of sugar are in there? Are the moles of sugar going to change? No, be the same before and after. Now we can solve this problem two different ways. We can use the dilution formula if we're careful, or we can do it this way and say, all right, how many moles of this do I have? Molarity times volume. Molarity times volume equals 4 molar times 250 milliliters. Notice I didn't change that to liters. If we multiply molarity times milliliters, the unit of measure that you get from that is millimoles. Okay. So 4 times 250 is 1,000 millimoles. Okay, how is that going to help us? Well, it saves us the trouble of changing that to liters. And if you divide millimoles by milliliters, you get molarity, right? I'll prove it to you. If you have X millimoles and you divide it by Y milliliters, what is that? Well, what's milli? Milli is 10 to the minus 3. Milli is 10 to the minus 3, right? If we cancel those out like that, right, they cancel. We get moles per liter, molarity. So millimoles divided by milliliters is molarity. All right, so this is how many moles or millimoles that we have from our original solution. What's the final volume? The final volume is this one plus that one. Right? Is that 626? 3, 6, 12, carry the 1. Yeah, milliliters. So if we divide 1,000 millimoles by 626.3 milliliters, then we'll get our concentration. And I get 1.5, let's see, 3 significant figures, right? Yeah, only 3. So I have to round. All right, let me round from my calculator. I'm going to round it to molar, 1.60 molar. That's B. Right? Now, how would we use the dilution formula? Well, let's do it that way also. In this case, we have, this is the concentrated volume, molarity. This is the concentrated volume. So now we need the diluted volume and the diluted molarity and the diluted volume. So what's this one? That's our unknown. What's this one? This one is 250 plus 376.3. Okay. So that would be our table, and we just put it into the formula, right? And we get the same answer. This is the trick right here. Understanding that the diluted volume is the initial plus whatever you added. All right, that was 13. Let's do 14 is ready to go. 14. You have 2 hydrochloric acid solutions labeled A and B. Solution A has a greater concentration than solution B. Which of the following statements are true? All right, let me scroll up just a little bit. All right, solution A and solution B. All right. So solution A has a greater concentration than solution B. So the molarity of A is greater than the molarity of B. That's given. Now we're going to look at each of the statements and see which one is true. Notice that when we get down to D, at least 2 of the above statements are true. Actually, E should be above D. because E says if you have equal moles of HCl in both solutions and so forth. All right, so D is out of place. It needs to be underneath. So we have to do A, B, C, and E to be sure that we have only one correct answer, or if we have possibly two, which would make D the right answer. Okay, what about A? A says, if you have equal volumes of both solutions, solution B contains more moles of hydrogen chloride. What does this mean? Molarity is moles per unit volume, right? Moles of A per volume, and moles of B per volume. Supposedly an equal volume. If they're equal volumes, which one has more moles? A does. If they're the same volumes, then this one has to be bigger in order for that to be bigger. Right? So A says B would have more moles. That means A is false. How about B? Adding more moles of HCl to both solutions will make them less concentrated. If you add more moles, this ratio increases for both of them. Right? So B is false. And it doesn't matter if we're talking about these solutions A and B or any solutions. When you add more moles of solute, you increase the concentration. C, to obtain equal concentrations of both solutions, you must add a certain amount of water to solution B. If we add more volume to B, what's going to happen to its concentration? If that volume increases, the overall decreases, makes it still less concentrated than A. So C is false. Then we go to E. If you have equal moles of hydrogen chloride in both solutions, equal moles. So these two are equal. If those two are equal, but they're still, this solution is still more concentrated than that one. But if you have equal moles, solution B must have a greater volume. Yes. If this has a greater concentration, notice, equal moles. Let's solve this for moles. N of A equals M of A and volume of A, right? And this one is moles of B equals molarity of B times volume of B. Okay, so now we can say if this A equals that B, correct? If this A equals that B, moles equals, then that means this one must be equal to this one, correct? Okay, but notice, if this one is bigger than that one, then that one has to be bigger than this one. If they're both equal, and this one is larger than that one, then this volume has to go down, this one has to go up. So you have more volume of B in order to make the number of moles equal. This one is true. All right, so there's only one right answer. All right, let's scroll to 16 and 17. A 116.9 gram sample of nitric acid solution that is 70% nitric acid HNO3 by mass contains how many moles? Okay, let's see, what do we have? 106.9 gram sample of nitric acid. All right, so the mass of the solution is 116.9 grams. Yep. And the concentration of the solution is 70%, or 70 grams of, is it nitric? Yeah, nitric acid. 70 grams of nitric per 100 grams of solution. That's what that means. How many moles of HNO3 do we have? Well, we can't get moles directly from that, but we can tell how many grams of HNO3 we have, right? If we multiply this times 116.9 grams of solution, right? These cancel and leave us with grams of HNO3. There you go. So let's do that calculation. We get 81.83 grams of HNO3. Now we need to convert that to moles. Molar mass. So hydrogen is 1.01, nitrogen is 14, and 3 times oxygen is 16. Okay. So this is 48 plus 14 and 1.01. 63.01 divided into 8183. And I get 1.2968 moles. But we only have what? 3 significant figures. So we got to chop it down to 1.30 moles of HNO3. That's why the answer is C. $17. All right. Determine the normality of a base if 93 milliliters of 1.8 molar HCl is required to neutralize 52 milliliters of it. Okay. 93 milliliters of 1.8 molar HCl is how many moles of hydrogen ions? We're looking for this because we're going to neutralize it with that. Right? So we need to know how much of this first. Right? 93 milliliters of 1.8 molar. 93.0, yes. And the concentration is 1.8 molar. 1.8 molar. Right? So 1.8 times 93 is 167.4 millimoles of hydrogen. Okay. So we need that many millimoles of hydroxyl. Right? In order to neutralize it. Oh, I made a big mistake. This is not 93 milliliters. Is it? The normality of a base, if 93 milliliters Oh, that's right. I had it right the first time. Oh, all right. 167.4 hydrogens, 167.4 hydroxyls. That's how many hydroxyls we have in 52 milliliters of base. All right, so millimoles per 52 milliliters will give us the molarity of hydroxyl. There we go. And we got three significant figures. 3.22 molar hydroxyl. Okay, that's molar hydroxyl. So what's the normality? Well, the normality is based upon how many hydroxyls can be produced from one molecule. Right? So this is the number of moles of hydroxyls. So that's equal to 3.2 normal of the base that produces those hydroxyls. And it doesn't matter, now that we know it's that normality, it doesn't matter which base we use. Whether we use sodium hydroxide, calcium hydroxide, aluminum hydroxide, doesn't matter. We know that we need this normality of any base to produce those hydroxyls. And we could have done the calculation by normality of the acid times the volume of the acid equals normality of the base times the volume of the base. And we get the same answer, right? Do it yourself. Plug those numbers in. Normality of the acid. Here. And volume of the acid here. Volume of the base here. Calculate the normality, and you'll get that number. All right. 17, 18. Okay. Magnesium metal reacts with hydrochloric acid to form magnesium chloride and hydrogen gas. Okay, might as well write that equation up here. Magnesium metal plus hydrochloric acid produces magnesium chloride in solution plus hydrogen gas. Okay. All right, so let's balance this equation. We got one magnesium, we need two hydrogens and two chlorines. That's good, we're balanced. Okay, now what's the rest of the question? Suppose we react an excess of magnesium metal. Excess. Okay. With 19.8 milliliters of 3 molar solution. 19.8 milliliters of 3 molar solution of hydrochloric acid. And collect all the hydrogen in a balloon. So we're going to collect all the hydrogen over here in a balloon at 25 degrees. Okay. 1 atmosphere pressure. All right. What's the expected volume of the balloon? Right. Volume is the question. All right. So we got excess here, so we don't need to know limiting. All of this is going to be used up and produce something over here. What is it going to produce? We know how many moles we start with. We know the ratio of the two. Then we can know the number of moles of hydrogen produced. That means we will have a value for moles. Remember, pressure, volume, temperature, moles, we can calculate the volume using this formula. Remember the gas laws? That's the ideal gas equation. Okay, so let's find out how many moles of hydrogen we need. 19.8 milliliters. Let's go ahead and convert that to liters. Since we're going to need to know moles anyway, let's go ahead and convert this to 0.0198 liters. Okay, then we multiply that times 3 molar. Remember, moles equals molarity times volume. So let's see, 0.0198 times 3 is 5.94 times 10 to the minus 2 moles of hydrogen chloride. How many moles of hydrogen does that represent? Well, what's the ratio? Our conversion factor is from the coefficients. So HCl down here, hydrogen up here, 1 there, 2 there. So we need to divide that by 2. 2.97 times 10 to the minus 2 moles of hydrogen gas. Okay, now we can find out the volume, right? If we solve this for volume, right, it's nRT over P. So the volume of our gas is going to be the number of moles times 10 to the minus 2 moles. R. What's R constant? It's in useful information, right? You can look it up. 0.08206 liter atmospheres per mole K. Temperature. Temperatures in degrees Celsius. We got to convert that to Kelvin. Right? So that's 298 K. Okay, then divide by pressure, 1 atmosphere. Okay, now we can determine the volume, and the volume is going to be in liters. Okay, I already got that one in my calculator, so I'm going to multiply times 0.08206 and 298 times that, and divide by 1, and I get 0.7, 3 significant figures, 26 liters. 0.726 liters. A is the answer. There you go. Next, 22. Which of the following solutions contains the smallest number of ions? All right. Notice that the last answer, at least 2 above, contain the smallest number. That means they have to be equal. So we've got to do all of them to find out if there are any 2 that are exactly the same. It's time for Henry Ford. Right? Set up an assembly line. So we got A, B, C, and D, correct? Yes. So 246 milliliters. How do we find out the number of ions? Well, first you got to find out the number of formula units, the number of moles of molecules. Then you say, how many ions does that produce each? Okay, so you got to know the formula for each one also. All right, so how do we find the moles? If we know the molarity and the volume, then we multiply molarity times volume equals moles. Right? Sodium sulfate. Sodium sulfate. That's a +1, that's a -2. We need 2 of those. And we have 246.8 milliliters times 1 molar. All right. That's going to give me millimoles, correct? Yes. Okay. Lithium nitrate. Lithium nitrate. -1 + 1. That's the formula. 539.8 milliliters times 1 molar. Okay. And then potassium hydroxide. Potassium hydroxide. -1 polyatomic ion +1 alkaline metal. That's the correct formula. 305.6 milliliters times 2 molar. Okay. And then 189.6, oh, iron 3 chloride. So iron has a 3+ charge with chloride there. So we need 3 here to balance the charges. Okay. 189.6 milliliters times 2 molar. Okay. This will give us the moles of compound. All right. 1 times this one, 246.8 millimoles. 539.8 millimoles of compound. 305.6. Okay, let's see, that's 2 and 1 10 11, carry the 1, 1 6 millimoles of compound. And 2 times this one. So that's 2, 12 there, carry the 1, 18, 19, carry the 1, 16, 17, carry the 1, and 4. There we go. So that's millimoles of compound. How about ions? What we need is another conversion factor. Right? For every compound, how many ions does it produce? Sodium sulfate breaks up into 2 + 1 is 3. Lithium nitrate breaks up into 2. Potassium hydroxide breaks up into 2. Iron 3 chloride breaks up into 4. There we go. Well, now what do we get? Well, let's see. 246.8 times 3 is 740. This is millimoles of ions. Okay. 539.8 times 2 is 1,080 millimoles. 611.2 times 2 is 1,222 millimoles of ions. And 479.2 times 4 is 1917 millimoles. Okay, so the least number of millimoles, least number of ions is A. Okay. That's what I mean by Henry Ford. We set up an assembly line, we do the same calculation for each one. Ready. Next. 25 and 26. Let's see. We're running out of time. And I'm running out of ink. Let's try another. Let's try another marker. Number 25. Go. Assume that vinegar is 0.852 molar solution of acetic acid. What volume of 0.2136 molar sodium hydroxide would be needed to completely neutralize 6.89 milliliters of vinegar? Okay. Notice that vinegar has one proton. Sodium hydroxide has one hydroxyl. So when they react, they're going to make sodium acetate plus water. And since there's one hydrogen for every hydroxyl, we can use molarity. Molarity and normality are the same for these two. So what we get is a situation where the normality of the acid times its volume equals the normality of the base times its volume. So what's the normality of the acid? The normality of the acid is the same as its molarity. 0.852. 0.852 normal. How about sodium? Sodium hydroxide. 0.2136. 0.2136 normal. Molarity and normality are the same for these because they have one proton, one hydroxyl. What volume of sodium hydroxide? So the volume here is what we're looking for. And the volume of vinegar is 6.89 milliliters. 6.89 milliliters. So we can plug it into our formula. Well, we can solve for base. Let's do that. Solve for the base. That means normality there, normality of the base. There we go. So normality of the acid is 0.852 times its volume, 6.89 milliliters. And the normality of the base is 0.2136. And notice, if we leave these as milliliters here, the answer is going to be in milliliters also. And that's what we want. So let's divide out these numbers, 852. 6.89 times that and divide it by 0.2136. So the volume of the base is equal to 27, three significant figures, 0.5. 27.5 milliliters. C is the answer. Okay, next, 26. 26, let's scroll it a little bit. There we go. For a reaction between 200 milliliters of 0.1 molar silver nitrate and 95 milliliters of 0.1 molar sodium chloride, the concentration of silver ions in solution after the reaction is complete is. Okay, so we go back, we got that same reaction we had before, sodium chloride and silver nitrate. All right, they're going to produce silver chloride solid, that's the precipitate. And what's left over is sodium nitrate in solution. Okay? So what we're given is 200 milliliters of 0.1 molar silver nitrate. 200.0 milliliters of 0.100 molar silver nitrate and 95 milliliters of 0.1 molar sodium chloride. There we go. So we need to find out which one is limiting. Because the question is, how many silver ions? What's the concentration of silver ions after the reaction? Do we have any of this left over? Right? So what's the total? This is, remember, this is balanced. So one of these for every one of those. This gives us 0.1 times that is 9.50 millimoles of sodium chloride. And this is 20 millimoles of silver nitrate. Okay? For every one of those, you need one of these. So this is limiting. You know what? I see a problem with this one. Let's see if I got my numbers right. 200 milliliters of 0.1 molar silver nitrate. Yes. 95 milliliters of 0.1. Yes. So that's 9.5 here. That's 20 there. Is that right? Yeah, that's right. So this is excess. One of these for every one of these. So minus 9.50 gives us here, and 9 from 19 is 10 millimoles of silver nitrate remained, which 10.5 millimoles of silver ions remain. Okay? This is excess. This is limiting. Right? Because they're 1-to-1. You're going to use all of these up, plus you're going to use up 9.5 millimoles of silver nitrate and leave you with this much silver nitrate afterwards. Okay? So which one of these statements is accurate? The concentration of silver ions in solution after the reaction is complete. Well, we can calculate that. Right? This many millimoles is also 10.50 millimoles of silver divided by what volume? 95 plus 200 milliliters. So 10.5 divided by 295 is 3.56 times 10 to the minus 2 molar. All right, we're not given exact values, but we do know that there is some silver left over. So which one of these statements comes closest? Let's see, A says 0.1 molar. That's not 0.1 molar. So A is wrong. A is wrong. How about B? Less than 0.1 molar. Wow, that's true. Less than 0.1 molar, because that's 1 times 10 to the minus 1. Yes, it's less than 1 molar. Some, but not all, of the silver ions are used to make the precipitate. That's true. So at this point, B is true. We don't have any oddballs in there. So we found the right answer. C says greater than 0.1. No, it's not. D says less than 0.1. Yeah, even though silver ions do not react, they are diluted when mixed. They do react. So D is false based on that statement. E, 0. No, we do have excess silver nitrate. Yeah, so we have excess silver. So B is the best answer. There you go. All right, that was 26. 26. Let's scroll. And I got 25 minutes. Let's see how many I can get done. 29. Okay. A nitric acid solution contains 71% HNO3 by mass. All right, so the concentration of HNO3 is 71% mass. Okay. Has a density of 1.42 grams per liter. The density equals 1.42 grams per milliliter, excuse me, not liter, grams per milliliter. How many moles of HNO3 are present in 2.36 liters of this solution? Well, the volume equals 2.36 liters. And the question is, how many moles are present? Okay. We can't use liters unless we take into account the density. So how many milliliters is that? 2360 milliliters. Now we can convert 1.42 grams per milliliter. That'll tell us the mass of the solution that we have. 2360. Yes, 1.42 times that. So we have 3.35 times 10 to the third grams of solution. Now we can find out how many grams of HNO3 that we have. All right. So if it's 71 grams of HNO3 per 100 grams of solution. And we multiply 3.35 times 10 to the third grams of solution, right? Grams of solution cancel. And 71 times that divided by 100, that is 2.38 times 10 to the third moles of HNO3. That's grams. 2.38 times 10 to the third grams of HNO3 is how many moles? Molar mass of HNO3, 1.01, 14 for the nitrogen, and 48 for the oxygen. Let's say 6301, 63.01, divided into that value. So I get rounded off to 3 places, 37.8 moles. That's A. Got to read my own questions, don't I? 29. Let's see what's next. 38. 38. You have two solutions of sodium chloride. One is 2 molar, the other is 5 molar. Okay, sodium chloride solutions. So solution 1 is 2 molar, and solution 2 is 5 molar. Yes. Okay. You've got much more 5 molar solution. And you add the solutions together. Which of the following would be the concentrations of the final solution? Okay, so the volume of 2 is much, much greater than the volume of 1, correct? If you put them together, this one's going to be diluted some by this one. But the concentration is going to be more toward this one because its volume is so much greater. Okay, so we need to find one of these values that's very close to 5, but less than 5, and far away from 2. So 7.2 is too big, right? Can't be. 3.5, maybe, that could be. We're looking for the best answer. 2.9 is too close to 2. It should be closer to 5, right? So it can't be that one. How about D? 4.8. That's even better. That's even better than this one. And 7, right? Same reason as this one, it's too big. So D would be the best answer, right? It would be the best answer of all those to account for the mixing of these two. All right. Oop, we did that one already. 50. Okay. What's the normality of 1 liter of sodium hydroxide solution that contains 18.2 grams of sodium hydroxide? All right. So the mass of sodium hydroxide is equal to 18.2 grams. And the volume of the solution is 1 liter. Okay. Now remember, sodium hydroxide only has 1 hydroxyl. So molarity and normality are exactly equal. So all we have to do is calculate the molarity, and we have the normality. So this needs to be converted into moles, correct? What's the molar mass of sodium hydroxide? Let's see, sodium is 23, oxygen 16, hydrogen's 1.01. 10, let's see, now is it 40, 40.01. Here we go. So let's see, 18.2 and divide by 40.01. So that's 0.455 moles. Okay, in 1 liter, moles per liter, molarity is 0.455 moles in 1 liter, which is 0.455 molar, which is equal to 455 normal. Okay, so the answer to that was A. All righty, let's see what's next. 52. We do this one before? Yes, we did this one before. That was already done. 55. There we go. In the following acid-base neutralization, 1.61 grams of solid acid C6H5O. Okay, so we've got the acid is C6H5O. I think that's actually phenol. 1.61 grams. Okay. Is neutralized 11.61 milliliters of sodium hydroxide solution. Sodium hydroxide. Right, this one's aqueous. And what are we given for sodium hydroxide? 11.61 milliliters. Okay. By this reaction. Okay, yep. And that produces water and sodium C6H5O. Okay. Yeah. Okay, we're good. Now calculate the molarity of the base. All right. This is 1 proton, 1 hydroxyl. So the molarity and the normality are exactly the same. If we say, well, first of all, how many moles of hydroxyl were required here? We don't know, because we don't know the concentration, right? We don't know the molarity of the base. All right, but we can figure how many moles of this acid were required, right? 1.61 grams. We need a molar mass for that acid, right? And we can calculate that. We have 6 hydrogens, 1.01 times 6, and we have 6 carbons, 12.01, and we have 1 oxygen, 16. All right, so 6.06 and 6 enter 12.01 times, add that together, and then 16. So I get 94.12. So divide that into 1.61, and we get 1.71 times 10 to the minus 2 moles of acid. Right here. That's the same number of moles of base, equals 1.71 times 10 to the minus 2 moles of sodium hydroxide. So now we have moles and we have milliliters. All right, so since we have moles here, we're going to have to convert this to 0.01161 liters. And then we divide this by 1 liters. That will give us the molarity. 3 significant figures, 1.47 molar. Is that correct? E is the answer. 1.47 molar. Okay, let's see if we got any more. 59. Running down to the wire. 59. What volume of 0.176 molar sodium sulfide solution contains 1.01 grams of sodium ions? Okay, 0.176 molar sodium sulfide. 0.176 molar sodium sulfide is what you have. We want to know the volume. The volume of that will yield 1.01 grams of sodium ions. 1.01 grams of sodium ions. So how many moles of sodium ions is that? Well, the electron weighs so little, the sodium ion, we can assume, can weigh the same as the sodium atom. So we use the molar mass of this one to find out how many moles of sodium. And that's 23? Yeah, 23. Okay. So that gives us the number of moles of sodium ion. 1.01, 23 is 4.39 times 10 to the minus 2 moles of sodium ions. Okay? So if we know the moles, okay, in order to use this value and determine the volume, right, from this expression, we need the moles of this compound, not the moles of ions. So we need to convert this to the compound. Right? So for every one of these, you have 2 of those, correct? Right, 2 to 1. So divide 2 into that. And we get 2.196 times 10 to the minus 2 moles of sodium sulfide. Now we can use that in this expression. Volume is equal to moles divided by molarity. So the moles are 2.196 times 10 to the minus 2 divided by the molarity, 0.176. And that's 0.1, 3 significant figures. 125. Liters. So is our answer in liters? Yeah, our answer is in liters. E is your answer. $62. All right. 15 milliliters of 0.3 molar sodium phosphate solution react with 20 milliliters of 0.2 molar lead 2 nitrate solution. What's the concentration of phosphate ions left in solution after the reaction? Okay, so we have sodium phosphate. Got to be able to write it. That's a 3 minus. This is a 1 plus. There you go. Reacts with lead 2 nitrate. That's a -1. This is a +2. That's why we have that answer. Now, what are they going to produce? Lead 2 plus and phosphate. All right. So just bring this 3 over here and that 2 over there. And we have a balanced formula. Now, the question is that dissolved in the solution or is it a solid? And you look it up in your chart, lead 2 plus and phosphate, and you find out it's a solid. What do we have left? We have nitrate and sodium. And that's definitely aqueous. Okay, now we need to balance the equation. You can set up your budget and balance the equation. But these types of equations are usually very easy to balance. We need 3 sodiums. Now we need 3 nitrates. Well, actually, that's the wrong place to start. Hold on a second. We need 3 leads, right? 3 leads. So that means we need 3 leads, 6 nitrates. Okay. Now we need 6 sodiums, 2 phosphates, 2 phosphates. We're balanced. Okay. Now that you've got a balanced equation, you can work the stoichiometry. 15 milliliters of 0.3 molar. 15 milliliters of 0.3 molar. Let's see, I put too many zeros. There we go. And lead 2 nitrate is 20 milliliters of 0.2 molar. 0.2 molar. Okay. The question is, what's the concentration of phosphate? So, do we have any phosphate left over? This is in solution. So we have to find out which one is limiting. So we need number of moles here. We can do millimoles. 0.3 times 15 is 4.5 millimoles of that compound. And this one is 4 millimoles of that compound. Okay. The ratio is 3 to 2. So if this is millimoles of lead to nitrate, right, and we want to convert it to sodium phosphate, sodium phosphate, the ratio is 3 here and 2 there. So what's that equal to? Well, let's see. 4 enter 3 divided 2 times is 2.67 millimoles of sodium phosphate are required to react. Okay? So all of this is going to be used up. All of this, if we use up all of that, it's only going to use up 2.67 millimoles of this one. So we'll have 1.83 millimoles of sodium phosphate remaining. Okay? That's left over. So this is limiting. And this is excess. So we will have some phosphate left over. We just need to find out what's the concentration. Okay, if this is millimoles of that compound, how many millimoles of phosphate is it? Well, for every one of these, you get one of those. So it's also 1.83 millimoles of phosphate ion. So how many milliliters of solution are we in? 15 plus 25. Let's do that again. 1.83 divided by 35. Now we got it right one. 0.052 molar. There we go. There is a right answer there. Your instructor just needs to pay attention to his own work. 62. Well, we're past 11. Let me see how many more we got to go. 64, 65. 65. We got 3 more to go. I'm going to try to finish them up here. 64. Because we got a late start. When a solvent has dissolved all the solute it can at a particular temperature, it is said to be, by definition, saturated. Okay. 65. If you mix 20 milliliters of 3 molar sugar solution with 30 milliliters of 5.57 molar sugar solution, you will end up with a sugar solution of, all right. So the way to solve this one is to go back to the original formula. Molarity equals moles per volume. What are the total number of moles of sugar? Well, we have 3 molar sugar times 20 milliliters. And we also have 30 milliliters of 5.57. Let's see, let's be consistent. 5.57 molar of 30 milliliters. That's the moles of sugar we have. What's the volume? The volume is 20 milliliters plus 30 milliliters. Right. So if we do that calculation, that's the thinking part. If we do that calculation, we should get the answer. By the way, where should that be, roughly speaking? The concentration should be somewhere higher than 3 and less than 5.57. Should be in between somewhere. So the answer is either A or E. Those are the only 2 possibilities. 3 enter 20 times, and then 5.57 enter and 30 times. Add those together. Incidentally, this is 227 moles. And divided by 50. So we get 4.54 molar. And that would be A. I think I got one more. Let's scroll to the last one, hopefully the last one. 74. $15 milliliters. Okay, we got lead 2 nitrate and sodium phosphate again. What's the concentration of nitrate ions left in solution after the reaction is complete? We don't need to write the equation up here. All we need to know is how much nitrate did you start with, because nitrate is still in solution after the reaction. How much nitrate? 20 milliliters times 0.3 molar lead 2 nitrate. Times, what did I say? 0.3 molar, 0.3 molar. Let's see, lead 2 nitrate. We better check that out. Lead 2 nitrate. We do need to know the formula, because this is going to produce 2 nitrate ions for every 1 compound. So this is the concentration, this is the number of moles of the compound. Right? 0.3 would be what, 6 moles of the compound. Yeah. But that's also 12 moles, actually millimoles of nitrate divided by what volume? Well, let's see. We put 15 milliliters plus 20. That's 35 milliliters. So that should give us the concentration of nitrate. 0.343 molar nitrate, which would be A. A is the closest one to that. Okay. That should be our last one. Let's scroll just to be sure. Yes, that's the end. End of the class, end of our review for today. We're ready for study the video, be ready for the exam on Thursday.